Hello, everyone. Uh, this is the live stream for what section are you? Physics 101A. All right. So let me see how many people are in the chat right now. I've got 7 people. There should be 10, or 8 now. There should be 10. So maybe before I start actually teaching, let me just ask you. Can someone just type in the chat box there, in the text box, if they can hear me? You should. I'm seeing that you can hear me, but I don't know. I've had some trouble earlier today. Just let me know. There's about a 30-second delay, by the way. So when you ask questions, just expect some delay before I actually answer them. So before I actually start teaching, I mean, I think you guys have the idea how the course is going to run. Your classes would have met. We would have met on Monday, Wednesday, and Friday. Um, we'll meet virtually on Friday, the way we're meeting now for a live stream. But Monday and Wednesday, I'll just give you videos to watch. Okay, I'll give them to you earlier, and you can watch them whenever you want. And they'll be like the lectures that I've given you up till now. And I try not to go quickly, but unlike when I teach in the class, I just lecture straight through, so they're pretty dense, and so don't be afraid if you have to watch them or stop and watch them a few times. I'll try to keep them under 2 hours to make sure that you can do that. Okay, and Monday and Wednesday, that's the asynchronous part of the course. You'll just watch videos that I've pre-recorded. Friday we'll have these live streams. You can ask questions during the live stream. And what I'm going to do, you'll see today, I'm just going to do problems. And the reason to do that is because the pre-recorded lectures, you'll see me, I do have problems that I go over, but the thing is that the problems are polished, and and they're already completed, and especially the diagrams. When I get to doing 1D kinematics, I'm going to be doing these diagrams. You saw already completed diagrams, which are pretty complicated, but there are steps in doing those diagrams, and so I'm going to show you those steps in real time. I'll use a different whiteboard that I'm using now, and I'll show you how to draw the diagrams, what steps to draw each of the parts of the diagram. And so that's why we really need this kind of synchronous time when we're together at the same time, and you're actually watching me as I do it and can ask questions. And of course, in the evenings, there's also the Google Hangouts that you can jump in. A few people have jumped in to ask some very short questions about how things work. Well, that's it. Okay. The only exception will be the week of the test, and we'll have nothing but live streams the week of the test because it'll all be review. I won't give you any new material. We'll just do problems that week. Okay. Let me just look at the chat here. I got to switch windows every once in a while. Oh yeah, I'm seeing some people saying, "Yep, you can hear me." Good. All right, so let's start. You should have watched 3 videos up to this point. The first one was on the syllabus and how the logistics of the course. The second one was on units and measurement, and we'll do 3 questions on that. Really easy stuff. You've probably done it in other classes before. I apologize, but I just had to make sure that everyone was on the same page with the units. And then the third video you should have watched was the introduction to a general theory of 1D kinematics. Okay, and I have a couple of sample problems that we can do there. Okay, so let's begin. Let's look at this first problem here. This is very similar to the one that I did in the lecture. Convert 100 kilometers per hour to MKS units. I think there I did 50 kilometers per hour, but it's okay. First, what are MKS units? In this course, we're going to use MKS units, which means for length measurements, we're going to use meters. For mass measurements, we're going to use kilograms, and for time measurement, we're going to use seconds. Okay, and there are 3. Well, there is actually 4 dimensions that you can measure in the universe: length, time, mass, and the 4th one that we don't need in this course is entropy. Okay, or information. But some of you might be chemistry majors, or it might even come up in biology. Entropy is yet something else that you can measure, and it's another dimension, but we don't need it this semester. Next semester I'll mention it briefly in the connection with temperature, but we don't need the units for that right now. Okay, so you take a look at this value here, 100 kilometers per hour, and you go, okay, well, what do I have to convert here? So you see here in the numerator, you got kilometers, And you say, well, what does that measure? That measures length, okay? But we don't want to measure our length in kilometers. We want to measure our length in meters. And so that's one unit that we're going to have to convert. In the denominator, by the way, in my text editor, I can't do like the vertical lines with the numerator on top and denominator on the bottom. So I have to do the sideways slash. So kilometers are in the numerator, hours are in the denominator. Hours measures time, but we want our units in seconds. And so we have to convert that too, okay? And so you begin by making equivalencies, okay? And so you say, okay, how do kilometers here relate to meters? And I like picking the bigger unit and expressing it in terms of the smaller unit. So you say, okay, 1 kilometer is 1,000 meters, like that, okay? And you should know the metric system and the metric prefixes. If you don't, I'll be introducing prefixes. You really won't need a lot of them. There'll be just a few, like kilo, centimeter, centi, and milli, and maybe a few others, but there won't be a lot. So, you'll be able to learn them very easily as we go along. So, you got 1 kilometer is equal 1,000 meters, okay? And that we'll use to convert our length unit. And then for the hour, for the time unit, we've got the bigger unit is hours, so 1 hour is equal to, and an hour is 60 minutes, and a minute is 60 seconds, so 60 times 60 is 3,600 seconds, like that, okay? So we're going to need these two conversions, and you say, well, how do I use them? Well, we're going to use this to create a fraction which is equal to 1. Okay, and there's two ways to do that. I can either do kilometers divided by the meters here, like that, okay? And that's equal to 1. The reason it's equal to 1 is because the numerator is equal to the denominator. And so if you have like 3 divided by 3, that's 1, or 7 divided by 7, that's 1. So whenever the numerator is equal to the denominator, which is what this says, that fraction is going to equal 1. That's one way to do it, but you can also do it the other way around, the flip of that, and put the 1,000 meters on top and the 1 kilometer on the bottom, like that. And both of those are equal to 1, okay? And the reason I'm doing that, the reason I'm forming this fraction 1, is because you can always multiply by 1 without changing a number, without changing the value of something. So if we start off with our 100 kilometers per hour. By the way, 100 kilometers per hour, that's like the speed limit on the highway. In Canada, if you drive on the QEW on the other side of the border, you'll see that the highway is marked in kilometers per hour, and it's 100 kilometers per hour. That's about 55 miles an hour. Okay, anyhow, so, we can always multiply by 1, and that's not going to change the value. Okay, and you say, okay, I've got these two fractions here. They're both equal to 1. Which one do I want? Well, you see here how the kilometers is in the numerator. Well, we want the kilometers in the denominator here, so they'll cancel against one another. So I'm going to take this one and I'm going to replace it by this fraction right there. And what that'll do is the kilometers here will cancel the kilometers there, and I'll be left with meters. So I'm replacing kilometers with meters, which is what I want to do. Okay, and we'll do the same thing with the hours. And so, you start off, you have to form a fraction like this, and you've got hours and seconds. You say, well, where do I want the hours? In the numerator here or in the denominator? And you see the hours here is in the denominator, so we're going to want the hours in the numerator. And so over here, I'll put the hours up here, and I'll have to put the seconds underneath there, like that. And I've done this so many times, this particular value, I know the answer. It turns out to be 27.8 meters per second. Notice the kilometers here will cancel the kilometer there, and the hour there will cancel the hour there. So the only units that survive are meters on top, seconds on the bottom, and you'll do 100 times 1,000 divided by 3,000, and that'll give you 27.8 meters per second. Okay, so there's our first example. Very easy. Okay, let me see if there are any questions in the chat. I have to switch between windows, so looking good. All right, there is a bit of a lag, so if I didn't see your question, I will after in a bit. Okay. All right, let's do the next one. The next one's a little bit more complicated, and it's different than what we did in the lecture. And it's actually a volume, and we don't need volumes this semester. We'll actually need them next semester, but it's still typical of the kinds of conversions that you'll have to do whenever you have like units squared or units cubed or something like that. Okay, so here this is a volume because it's a length times a width times a height. Okay, so whenever you multiply length times width times height, you get a volume like that. And so you've got centimeter times centimeter times centimeter. Okay, now the first thing we'll need is converting between centimeters, which is a length unit, and meters. And so picking the larger one, 1 meter, is equal to 100 centimeters, like that. Okay. By the way, you could do it the other way around. You could express the smaller unit in terms of the larger unit. So you could go 1 centimeter is equal to 0.01 meters, and both will work just the same. You'll get exactly the same answer. This equivalency is the same as that one. You just divide both sides by 100. So if you divide, 100 centimeters by 100, you get 1 centimeter, and you divide 1 by 100, you get 0.01. Okay, so they're both identical. I just like doing it that way because, I don't know, I just like to avoid fractions, okay? And so we're going to use this, but let's be careful how we use it, because now we have this, and we have centimeters cubed. By the way, I can't do superscripts. This is just a plain text editor. So I do use the little caret like that. A lot of calculators do that too. And that just means cubed. Okay. So what do you mean by cubed? Like if I say centimeters cubed, what does that mean? That means you have centimeters times centimeters times centimeters. Okay. And so I can replace the centimeter cubed by centimeter times centimeter times centimeter. So there's 3 centimeters there. Okay. So let's go ahead and form that fraction. And there it is. There's the fraction. You got to decide, where do I want, what do I want in the numerator? What do I want in the denominator? Well, we want to get rid of centimeters. So we want the centimeters in the denominator, and we want the meters in the numerator. And you might think you're done, but you're not. This, because there's only 1 centimeter here, and that'll only cancel one of them there. Okay, so 1 centimeter there cancels 1 there. You've got 2 more, so actually you have to multiply by this 2 more times. Let me see if I can copy and paste, and paste like that. So you actually have to have 3 of the, you have to have the conversion fraction 3 times, because one of them, this one, will cancel out the first centimeter and replace it with meters. This one will do the next one and the next one like that. Okay, so this is just a little bit more subtle, and so you just be aware of that, so that if you've got like centimeters squared, centimeters cubed, on this semester we'll have seconds squared, so you may have to convert the seconds twice, okay, or time unit twice. And there it is. Okay, so just to go over that again, the centimeter here will cancel one of those centimeters there. The second centimeter there will cancel the second centimeter there. And the third centimeter there will cancel that one there. Okay. And so now we have the numbers, and we have the surviving units are 1 meter, 2 meters, and 3 meters. And that'll give me an answer of, let me grab it. All right. And there will be 1 meter, 2 meters, and 3 meters. So it'll be like meter, meter, and meter, but we don't usually write meter, meter, meter. We write meter cubed like that. Okay, and there's the answer to the second one. So just a little bit more complicated. All right, let me see if there's any questions in the chat. Oh no, the screen went blank. How did that happen? I'm so sorry. I'm not sure where I left off. I've had nothing but technical problems today. Let me go quickly over the second question. I'm taking a look here, and I could see that it's kind of come back here. But let me just go over the second question. I should look at the chat more often. All right. Well, let me just let me see if this is showing up here. Wow. We missed the entire problem. Okay, thank you, Candace. Let me repeat it very quickly. So it was the second problem, right, that you missed? Is that correct, or the first problem? All right, hold on here. I think I know what. I think I can see what might have happened. This is very rare, seldomly happened. Okay, I'm going to do the second problem again. I'm assuming, yeah, it was the second problem. Okay, thank you guys. All right, so what happened here is, yeah, and I could see that the leg is actually decreased right now. All right, so in the second problem, I have the 7,500 centimeters cubed. Okay, and I have that 1 meter is equal to 100 centimeters. Okay, that's what a centimeter is. There's 100 centimeters in a meter. You could also write that as 1 centimeter is 0.01 meters, which is the same. You just take the 1 and divide by 100. But I like the first way of doing it because I just like expressing the larger unit in terms of the smaller unit. Okay, and whoops, let me just put my centimeters back in here because I cancel them out like that. Okay, so so the centimeters cubed I wrote as centimeter times centimeter times centimeter, and the conversion fraction we need it 3 times, and the reason is that one of the first conversion factor will cancel out the first centimeter, the second conversion factor will cancel out the second one, and the third conversion factor will cancel out the third one. Okay, so unlike the previous problem where you only had to multiply once, here you have to multiply 3 times. Okay, and you'll notice that one of the centimeters will cancel out one of them. The second centimeter will cancel out the second centimeter here, and the third one will cancel out the third centimeter there. Okay, and what you'll be left here is a meter, a meter, a meter, and so you get meter cubed. Okay, and then if you multiply out the numbers, it's like 7,500 multiplied by 1 over 100, multiplied by 1 over 100, multiplied by 1 over 100. And so that works out to be 0.0075 meters cubed. Okay, so I went a little bit quicker, but I think you know that should be good. I mean, I know it's not as good. I was speaking with a black screen, but um, it must have happened when I switched windows. Okay. All right. Well, let's go on. If I went too fast over that, I can go over it again. But let me go on to the third problem here. Okay. And this third problem is actually not something that we'll wind up doing in this course, and that is converting from pounds to kilograms or inches to meters or things like that. But I wanted to show you this because this technique of converting extends to all possible conversions. You might as well know how to do this for other courses as well. So here I say convert 13 lbs, that's pounds, to MKS units. Okay, so pounds measures weight, and the MKS equivalent unit is kilograms. Okay, and you go, but I don't know the conversion in there. Right. So what you can do is you can actually Google for it. And Google's very good about this. Oh, I lost it again. Google's actually very good about this. Let me actually show you. There, the Google screen should have actually come up now. Okay, so if you just put in your Google bar, convert pounds to kilograms, and or you can even put calculator there, but it's just sufficient to put convert pounds to kilograms, then and search for it. What will happen is it'll bring up the equivalency that you need, and so you could see here in the browser, it says 1 pound is equal to 0.453592 kilograms. So, you know, I mean, I'm doing this for pounds, but you could do it for any units at all. Like you could say, convert from centimeters to meters, convert from meters to centimeters, although that one's easy. You know, convert from kilograms to micrograms. That one's a little harder. Okay, and you can do all of that just by, you can get that fraction just by Googling for it. Okay, so I wanted to show you this example for that reason. All right, let me switch back to my other window here. Okay, and so here we have convert and 13 pounds, and let me just copy and paste that conversion factor over. Okay, all right, like that. And so 1 pound is equal to 0.453592. And now what do you want to do? Well, now you want to take the 13 pounds like this and multiply by our conversion fraction. Okay, and since the pounds are in the numerator, we want that in the denominator, so we'll take that one and put it in the denominator there. Whoops. And we'll take this number here and put that into the numerator like that. Okay, and you'll see that the pounds and the pounds here and the pounds there will cancel, and the answer is let me get that, do the calculation very quickly. It's kilograms. Okay, So again, I won't expect you to convert pounds and stuff like that, but I just wanted to show you that you can do any conversion by this technique. And if you don't know this fraction here, the equivalency, you could just Google for it, and you could just say like convert pounds to kilograms or whatever you need. Okay, so I think that's enough for this. Let me see if there are any questions. And okay, good. And thanks again for pointing that out to me. I should probably look back and forth at the chat more often. All right. So let's go on and do our kinematics problems. Okay. So the kinematics, what is that? What is kinematics? It's giving a mathematical description to motion. Okay, so like if something is moving, like say a car is moving down the street and it comes to a halt, we're not so much worried about asking why did the car come to a halt. That's questions of dynamics, and we'll do that later. That's answered by Newton's laws. All we want to do is just describe, like, how did this, describe the motion as the car comes to a halt. Okay, it's like, how did it come to a halt, like as a function of time? And so in doing that, I had to introduce the concept of velocity and the concept of acceleration, where the velocity is the rate at which the position changes and the acceleration is the rate at which the velocity changes. But in doing that, I had to introduce two concepts of velocity and two concepts of acceleration. And let's just look at the velocity. The two concepts are the average velocity and the instantaneous velocity. Okay, so the average velocity is mostly what you talk about, like you do this whenever you're taking a trip. You say, like, how long was the trip? Like, how much distance did you travel in a trip and how long did it take you to travel that? So for instance, if you drove 30 miles and it took you half an hour to drive 30 miles, well then you were on average driving 60 miles per hour. Okay, that doesn't mean you were always driving 60 miles per hour. You might have been driving a little bit faster, a little bit slower. Because it's an interval of time, a finite interval of time, your velocity can change during that time. The instantaneous velocity can change during that time, but the average velocity is just whatever that is. And that's what this first question is about. The instantaneous velocity comes out of the average velocity by taking that time interval and making it smaller and smaller and smaller and smaller and smaller, making it so small that it becomes an infinitesimal, a point. And so that requires calculus. Basically, that's a limit. Okay, and so that'll be our second question. Our second question will be, how do you get instantaneous velocity? Now, in my previous class, someone asked, how do you know if you're talking about average or instantaneous velocity? How will you know? If I didn't use the word average here, how would you know? An average velocity is always calculated over an interval. So you can see here, I say, what is the average velocity during 0 seconds to 1 second? That's an interval. Whereas when I ask for an instantaneous velocity, that's at just one point in time. Okay, that's the difference. So the instantaneous velocity is at one point in time because what you did is you took that time interval, the delta t, and you made it so small that it just shrunk down to a point. Okay, and the details of how the limits work, well, that's part of calculus. I could explain it, but I assume that you already know how that works. Or if you don't, then that's something that you will get out of your calculus. Okay, so let's do the first problem. A car is found to be at the following positions at the given times. So at 0 seconds, this car is at position 2.5 meters. What does that mean? That means that I have a reference point, which I didn't specify in the problem. But if you remember from my lecture, I had that tree. I said, you know what? The tree is the origin. We're going to measure everything with respect to the tree. Okay. So once you pick your reference point, that becomes your origin. You measure everything to that reference point, and you don't change that afterwards, otherwise you confuse everything. Okay, so this car is like 2.5 meters from whatever our reference point is, and then at 1 second it turns out to be at 3.1 meters, and then at 2 seconds it turns out to be at 3.9 meters. You just measure it, and then at 3 seconds it's at 4.9 meters. You're actually going to do this experiment in the lab, though not with a car. You're going to use this linear air track, and you have this glider on top of a linear air track, and the air track, it's kind of triangular shape, and it shoots out air, which makes the glider float on top of it, and then the glider can move without friction. And you're just going to say, where is the glider at different times? Okay, you'll actually use the computer with these photo gates to help you measure it accurately, and so you'll get a chart which looks very much like that, a table which looks very much like that. You'll have 0 seconds, where is it, 1 second, 2 seconds, 3 seconds, or maybe tenths of a second, but it'll be some finite intervals. Okay, you can't get instantaneous velocities out of this information because where it was at 0 seconds, where it was at 1 second, but where was it at half a second? Where was it at 0.25 seconds? Where was it at a tenth of a second, at a hundredth of a second? Since you don't know where it was in between, you can't shrink that interval down. And if you can't shrink the interval down, you can't get an instantaneous velocity. Okay, so this whole question is about average velocities. So let's do it. All right. So the first question is, what is the average velocity during the time the interval 0 seconds to 1 second? And for that, you're going to use this formula right here. I'm just going to cut and paste it from another like that. Okay. Oh no, it went blank again. This time I checked. I don't know why it's doing that. It didn't do that before. Something must have changed. Okay, I got it back. Okay, I'll make sure to be very attentive to that, so it won't happen again. Okay, so basically the formula for average velocity is v is equal to delta x over delta t. Now, in my editor, I can't do that triangle for the delta, so I'll just write out the word delta. And I also can't put a bar on top of the v for, like, usually when you do an average velocity, you put a bar on top of it. But there's the formula there. Okay, so it's delta x over delta t. So delta x means how far did it travel, and delta t is the duration of the interval. Okay, so to get a delta, it's always the final minus the initial. And so here we're looking at 0 seconds and 1 second. The final is the 1 second. You say, well, where is it at 1 second? It was at 3.1. Where is it at 0 seconds? It was at 2.5. So the delta is going to be the 3.1 minus the 2.5. Okay, so let me put that in there. So it's going to be 3.1 meters minus 2.5 meters, like that. And there's your delta x. Okay, there's your delta x. All right, so now what about your delta t? Well, your delta t is the same thing. It's going to be the final time and the minus the initial time. Imagine you have like a stopwatch, and as you're watching the motion, your stopwatch says 0 seconds, and that's at 2.5 meters, and then your stopwatch says 1 second, and that's when it's at 3.1 meters. And so the time interval is the 1 second, the final time reading minus the initial time reading. Okay, so well, that's kind of trivial. It's 1 second minus 0 seconds, like that. Okay, and what does that turn out to be? 0.6, and the units are meters divided by seconds, like that. Okay, all right, so that was the first one. Let me do the next one. It's pretty straightforward. It's the same idea. Okay, so what is the average velocity during the second time interval? All right, and now we are going from 1 second to 2 seconds. So let's look at that chart again. At the 1 second point, that's our initial, we're at 3.1 meters. At 2 seconds, that's our final time, we're at 3.9. So it'll be the delta x is 3.9 minus 3.1. 3.9 meters minus 3.1 meters, like that. Okay, and the delta t is going to be the final time reading, which is 2 seconds minus 1 second. It's still a 1 second interval, but it's shifted from the previous 1 second interval. Okay, it's going to be 2 seconds minus 1 second, like that, and that'll turn out to be 0.8 meters per second, like that. Okay, all right, so during the first time interval from 0 to 1 second, our average velocity was 0.6 meters per second. During our second time interval, which is also 1 second in size, but now it's from 1 second to 2 seconds, our average velocity was a bit faster. It's 0.8 meters per second. Okay, and then finally, let's do that for the third one, from 2 seconds to 3 seconds. Okay, and that's going to equal, well, now our final position will be, our final position at the 3 second point is 4.9 meters, and our initial position was 3.9 meters, so it'll be 4.9 minus meters minus 3.9, like that. Okay, so there's our delta x, and our times are going to be, the final time is 3 seconds minus 2 seconds, so it's 3 seconds minus 2 seconds, like that, and that's going to equal 1.0 meters per second. Okay, all right, good. Let me take a quick look at the chat if there's any questions. No questions so far. Good. Oh, and I lost it again. I've never had that happen so many times. It's happened occasionally, but never this many times. I'm not sure what's changed, but I'll just keep my eye on it to see what might be happening. Okay, anyhow, so there we go. That's these were average velocities, but notice that even the average velocity between each of the different time intervals changed. Okay, so we originally had during our first 1 second interval 0.6, to our second 0.8, and our third was 1 meter per second. Okay, and that's velocities, how fast it's going. Acceleration, I didn't ask you for average acceleration, and I won't ask you for average accelerations calculated from average velocities. That gets a little bit messy, and it's actually going to be done in the lab, and it's not that interesting for the rest of the course anyhow, so it's not like you're missing much. So I'm not going to ask you to calculate average accelerations this way, but we can see acceleration in this problem. I made the numbers to show that the car was accelerating. You see the car started off at 0.6 meters per second. It sped up a second later to, on average, 0.8 meters per second, and then another second later to 1 meter per second. So you can see that it's getting faster and faster and faster. And now you ask, by how much did it speed up? Well, from 0.6 to 0.8, it sped up by 0.2 meters per second, and from 0.8 to 1, it sped up again by 0.2 meters per second. So it's speeding up 0.2 meters per second. Okay, and that gives us an acceleration of 0.2 meters per second squared. All right, so I didn't ask you to calculate that, but since we're here, I might as well show you how average accelerations come out of this. Okay, and again, it's an average because it's over a time interval. It's a 1 second, like 1 second later the velocity has increased. So the average acceleration over that 1 second was 0.2 meters per second squared. Okay, so again, velocity is how fast you're going. Acceleration is how much you're speeding up. And so for acceleration, you have to look at the changes in your velocity. Okay, finally, the last question was, calculate the average velocity over the entire trip. Okay, and the way you do that, that's from 0 seconds to 3 seconds. So you don't, because your time interval is finite, you can make it as big as or as small as you want. Okay, you don't have to make it smaller. You make it smaller, infinitesimally small, if you want the instantaneous. But if you want an average, like, I don't know, you're taking a trip across the country, you might want to say, well, how many miles per day did I drive? Okay, that's a perfectly legitimate average number. But it's actually making the interval even bigger. Okay, so, and that's totally legitimate. You're just answering a different question. Okay, so here is I want the average velocity over the whole trip. That's from 0 to 3 seconds. Same, it's the exact same formula, like that. Okay, and now our delta is going to be, our delta x is the final position, which is 4.9 meters, minus our initial position, that's at 0 seconds, which was 2.5. So that's like, the full trip. Okay, and divided by 3 seconds minus 0 seconds, like that. Okay, and that turns out to be 0.8 meters per second. All right, there you go. Okay, so the average over our entire trip, the average velocity was 8.8 meters per second. Okay, before we move on to the next one, ask yourself, does this make sense? And it does. I mean, your average always has to be between your minimum and your maximum. Okay, so if you've got you're taking a trip and you've got some velocity that fluctuates, okay, your average can't be below your slowest velocity, and it can't be above your fastest. Okay, it's got to be somewhere in the middle. And if you remember, our velocities fluctuated between 0.6 and 1, so the average has to be between there, and it turns out to be 0.8. So yeah, that does make sense. If you would have gotten here an average velocity of, say, 1.2 meters per second, but you were never even going 1.2 meters per second even once during that interval, you did something wrong. Okay, so that's why it's good to ask the question, does it make sense? Because if it doesn't, then you might have done something wrong. Okay, so that's it for average velocities. It's pretty simple. Okay, let me see if there's any questions in the chat. All right, you're looking okay. I don't see any questions there. And haha, I lost it again. It's okay. Yeah, something has changed. All right, that's okay. We'll keep an eye on it. All right, last question. All right, last question is, this is about instantaneous velocities, okay, or it's going to involve instantaneous velocity and even instantaneous accelerations. By the way, after this, we'll only be working with instantaneous velocities. So I'm going to stop saying average and instantaneous velocities. If I have to distinguish the two, then you'll hear me definitely say instantaneous versus average, okay? And so on a test or on one of your assignments, if I want one thing over the other, I'll be very, very clear about it. But, as the course goes on, average becomes less interesting than the instantaneous, okay? So here we have this problem where I say the height of an object above the ground is given by this equation right here, okay? X is equal to -2t squared plus 5t plus 10, okay? And assuming MKS units, of course, okay? And this x, it's actually a function of time, so I could have written like x of t like that, but I didn't because I could have, but I just want to make sure that you people understand that this is not x times t. That just means x depends on the time, okay? And so you plug in a time here, and you'll get a value of x. So there's a value of x at every single instant of time. That's over an entire continuum, okay? And so that means that now, unlike our table above, where we couldn't shrink it past a 1 second delta t, here we can shrink the delta t down smaller and smaller and smaller, okay? And so we can actually shrink it down to an infinitesimal, in which case your delta x over delta t becomes the derivative, dx over dt, okay? We'll see that when I get to part B here. But let's do the first question. How high is the object above the ground at t equals 1 second? Okay, and so that's exactly what this is actually giving you. Okay, so let me get rid of this right here. At 1 second, at t equals 1 second, all you do is you take the t there and you just replace it with 1 second. Okay, I mean, you guys know this is it's just how you work with functions. Okay, so where is it at t equals 1 second? Take that t out of there and replace it with 1, and take that t out of there and replace it with 1, and so now I have 1 squared, and 1 squared is just 1, so I have 2, and 5 times 1 is 5, and plus 10 like that, and so that's going to equal 13 like that, okay? And so we can just put a little English here to be very clear. At t equals 1 second, the object is 13 meters above the ground, okay? All right, how's that? Okay, so the ground here is like our origin, okay, and we're measuring upwards, okay, for a height, all right? And so at t equals 1 second, the object is 13 meters above the ground, all right? So that was easy. Now, the next one gets a little harder because now I ask how fast is it going at t equals 1 second, okay? Now, first, I must be asking about an instantaneous velocity. And the reason is because I say at just 1 second. I didn't say over an interval of time. I said at one particular point in time, at 1 second, okay? So that's one reason you should know that it's an instantaneous velocity. But I could even just, I could have even just written here, how fast is it going? All right, instantaneous velocity at t equals 1 second, all right? Like that. Now, you look at this and you go, well, I didn't give you the velocity as a function of time. I gave you the position as a function of time. But like I just said a minute ago, if you do delta x over delta t and you shrink the delta t down to 0, that delta x over delta t becomes dx over dt. Okay, and so maybe I should just write that. Okay, so if you have like delta, so your velocity, your average velocity is delta x divided by delta t like that. Okay, but now, so this is average. But now you could say, well, the instantaneous is the same, but delta t is very, very small. And how small? Limitingly small. Okay. In mathematics, you can make it as small as you want. You say it's not small enough, I can always make it smaller, because you can always find a number which is smaller than the number you already have. So you can always make the delta t very small. In physics, practically, as soon as you hit the limits of your instrument, so that making it any smaller, you can't possibly measure it, you've pretty much hit the limit. Okay. So delta t is very, very small. Now, when you do that, we don't write delta x over delta t very, very small. We write, using calculus notation, b is equal to dx by dt like that. Okay, so there it is in calculus notation. Basically, the velocity, the instantaneous velocity, is the first derivative of the position function as a function of time. Okay, and you do not have to know how to differentiate. There's just a few things that you have to know how to differentiate. You have to know how to differentiate t squared with respect to t. Okay, and if you do that, it turns out to be 2t. If you don't know why, well, then refresh your calculus. Okay, and look at your calculus textbook. And you do need to know how to what uh, dt. I don't know why I put a space in here like that. So what's dt by dt? Well, that's just 1. That's pretty obvious. And then you also have to know what happens when you differentiate a constant with respect to time. And that's 0. And that's easy to understand because, if you've got a constant, like say 5, or in this case, it's going to be 10. Okay. At one time, t equals 0, it's 10. At t equals 1 second, it's 10. At t equals 2 seconds, it's 10. It's always 10. Well, how much is that 10 changing over time? It isn't. It's always 10. And so if it's never changing, the rate at which it changes is nothing because it's not changing. And so whenever you take a constant and you differentiate it with respect to time, you get 0 like that. Okay, so in the function here, let me just rewrite the function so you could see it again. I don't have to keep scrolling up and down. Like here, like that. Oops, cut and paste error. There we go. Okay, so in the function here, you'll see you have a t squared here, and when we differentiate that, we'll get 2t, and we have a t here, when we differentiate that, we'll get 1, and we have a 10 here, and when we differentiate that, we'll just get 0. And so what we get, if we go dx by dt, we'll get -2, and then that t squared becomes 2t, and then plus 5, and that t becomes 1, and the 10 becomes 0 like that. And so this reduces to, so remember the dx by dt, that's v. Actually, I'll write it. Dx by dt is equal to -4t plus 5. Okay, so this now tells you the velocity at all different times, at all times. Okay, and I asked for the velocity at t equals 1 second. So at 1 second, you can just substitute in there 1 second. So you got v is equal to, here, let me just rewrite this like that. Okay, and you go, but I don't want it at any old time. I want it at t equals 1. So you take that t there, just replace it by 1, and this is going to equal 1. So at t equals 1 second, the velocity is understood to be instantaneous velocity is 1 meter per second. Okay, so there you go. There's an example of finding the velocity. I gave you the position as a function of time. You have to find the velocity. Differentiate and then substitute in any time. Okay, let me see here. All right, chat is quiet, so seems people are doing good, and it happened again. All right, so let me. Okay, and then the final question is what is the acceleration at t equals 1 second? So the acceleration, let's go to the average acceleration first. The average acceleration is equal to the delta v, the rate at which the velocity changes. So it's delta v divided by delta t. Okay. So remember when we were looking at the previous problem, question number 4, remember how I said, well, it changes from 0.6 meters per second to 0.8 meters per second. And so we said, well, what was that change in there? That's your delta v. Turned out to be 0.2. Okay, so 0.2 meters per second. So it's how much did the velocity change divided by how long it took for that velocity to change. Okay, now this is average, and I should put a little bar over the a to say average. But you say, well, how do I get then the instantaneous? So this is average. How do I get the instantaneous? Well, same thing. You just shrink the delta t down to 0, and this becomes dv by dt like that. Okay, so in other words, you differentiate. Okay, so now I need the function v as a function of time, velocity as a function of time, and that's exactly what we got in the previous problem. Okay, and so let me just write the v as a function of time down here. That v is equal to that. Okay, and so if I do dv by dt, I'm going to differentiate the t, and dt by dt is just 1. Okay, and so I get equals -4 times 1 plus, and 5 is a constant, so a constant derivative of a constant is 0, so that 5 contributes nothing to the derivative, and so this is just going to equal -4 like that. In other words, the acceleration is a constant, -4. Okay, so that doesn't always happen. In this particular problem, I made that the acceleration doesn't change over time, and that's fine. It means that the the acceleration is -4 at 0 seconds, at 1 second, at 2 seconds. At all time, the acceleration is -4. So that doesn't change. Okay. So you could just conclude by saying at all times, a is equal to -4, and the units are meters per second squared, like that, including, of course, t equals 1 second, because that's what I asked up here. I said, or right here, what's the acceleration at t equals 1 second? Well, it's -4 meters per second squared at all time, including at the 1 second mark. Okay, so that's how you solve problems like this. All right, let me look here in the chat. Everyone seems to be doing okay. No questions. So we're almost done. Haha, it happened again. I think I know now why it's happening. So whenever I switch back to the chat, for reasons that I don't understand, because it didn't happen earlier, it's never happened before actually. So, okay, anyhow. So there it is. If I don't see any questions, we'll be done. But let me just tell you a few more things. About how the course will work. Over the weekend, I'm going to prepare your first assignment. Your first assignment will be questions very similar to this, okay? And I don't know, there'll be like maybe 3 or 4 questions. Now, some of the questions might have several parts to them, okay? So like question number 5 here had a part A, B, and C, okay? So because each question has kind of a, how should I put it, it's like one theme. There won't be a lot. I'm going to guess that it'll take you, like, how long did this take us? 45 minutes, and I'm going very slowly. So I don't think this will take you more than half an hour. These assignments will take you more than half an hour. The point is to make sure that you're keeping up with the course, and also to kind of know what kinds of questions you're going to get on the test, so that you're ready. Okay, you won't be when you get to the test. If you've done the assignments, you won't be surprised. You shouldn't be surprised. Okay, and well, there it is. Okay, so let me see if there's any questions. If not, we're done. Okay. Yeah, I don't see any questions. Is everyone okay then? I'll wait about 30 seconds, and if everyone is okay, then oh, I've seen the first answer. Looks like the leg problem has kind of cleared up. Let me just chat in here. Is everyone okay then? We can end the stream. All right. Yeah, I'm not seeing any other questions. All right. Bye-bye, everyone. The reason I'm shaking, by the way, is so that because there's a leg, I'll see when I finally see the shake, and then I know that I've said everyone has seen my goodbye. All right. Okay, end of the stream.